Hello everyone. In this video, let's learn about very important type of flip-flop beside the D flip-flop, which is the JK flip-flop. In this lecture, we're going to learn how we can design the circuit from a SR flip-flop using NAND gates, and also we'll learn how we can obtain the truth table for JK flip-flop. So in previous videos, we saw that how we can design the SR latch using NAND gates, and also we learned how we can obtain the truth table for it. Also, we saw how we can design the circuit for the SR flip-flops using NAND gates as follow, and also we obtained the truth table for it. And here at the bottom, I listed the truth table for 3-input NAND gate because we're going to use it when we design the circuit for JK flip-flop. So technically, we can take this SR flip-flop circuit and modify it to make it JK flip-flop. So let's do that. Let's take a copy of this SR flip-flop and modify it to make it JK flip-flop. So now to modify this SR flip-flop circuit and make it JK flip-flop, we need to make these two NAND gates 3-input. So let's have another input, call it J. So this one will get rid of the S. This is one input, and this is our J input. And then this one here is, we make third input, well, let's call it K. And now where do we get these two inputs from? So simply we can take this Q bar from here and feed it into this third input of the NAND gate. And also we can take a Q, branch it, and feed it to as a third input to the bottom NAND gate. So now this whole circuit here becomes our JK flip-flop. So it has 3 inputs, J, K, and the clock, and 2 outputs, Q and a Q bar. So next, let's design the truth table for it. So we have the clock here. We have a J input. We have K input. And then we can get Q and Q plus. Q is the current state, Q plus is the next state. So let's focus on JK inputs first. So all the possible combinations could be, we could have 0, 0, but the current state, because we want to analyze all possibilities, so the current state of the system could be 0 and could be 1. So that's why each combination we write it twice. And then the next possibility is to have 0, 1. So we'll write it twice because the current state could be 0, could be 1, and then 1, 0. Also we want to write it twice because the current state could be 0, could be 1, and then 1, 1, we write it twice because the current state could be 0, could be 1. So in this case, in this scenario, we're going to assume the clock is disabled. So now we want to figure out what will be the next state. So let's do this. Let's refer back to our circuit. So in the first row, we're assuming the current state of the system is 0. So that means Q is 0. So this Q will go in 2 locations. So we'll come here to this NAND gate. So this will be 0. And then also, as we saw, it's going back to this NAND gate. So this is 0. The clock is 0. And then for the first row, we have J is 0 and K is 0. So this is 0, this is 0. For the bottom NAND gate, we see that we have 3 inputs of zeros. So if we refer back to our NAND gate table, truth table, with the 3 inputs, when we have 3 inputs of zeros, the output will be 1. So that means R bar will be 1. And now 0 and 1 for this NAND gate. So the output will be, for the AND gate, if we get 0 and 1, the output is 0. But for the NAND gate, the output will be 1. So this Q bar will be 1. And this Q bar will go in 2 locations. It'll go here, and also it'll go all the way to this NAND gate. So this is 1. So now for this top NAND gate, we have 3 inputs, 1, 0, and 0. If we go back to our truth table here, so we have 2 zeros and 1, the output will be 1. So this S bar will be 1. Now, S bar is 1 and R bar is 1. If we look in our latch here, when S bar is 1 and R bar is 1, so we hold the previous state. So if you complete all the combinations the same way as we did here, you're going to notice all of these here will be, the next state will be hold. It will hold the previous state. So all of these will be the same when the clock is disabled. We can try one more and then you can practice with the rest on your own. So let's try this one just to ensure we're gonna get the hold state. Okay, so for this case, we have a j is 1 and k is 0. So that's a j is 1, so that's k is 0. And the clock is disabled. So now the current state, we notice here q is 1. So we start with 1, and then we want to see what will be the next state for q. So this one will go into location. It'll come here, and then it'll come as an input to this NAND gate. And so now we completed the inputs for the bottom NAND gate. We have 2 zeros and 1. So from the table, the output will be 1. So R bar is 1. For the NAND gate, when we have two inputs, 1 and 1, so the output will be 0. So this Q bar will be 0. Now Q bar will be an input for the top NAND gate. So the top NAND gate, we have 2 zeros and 1. When we have 2 zeros and 1, the output is 1. So S bar is 1. So as we saw, S bar is 1, R bar is 1. So we are following this case here. So we have also hold. So now let's do the same thing, but instead of the clock disabled, we want to see what happened when the clock is enabled. So let's copy this table here. So now instead of the clock is 0, we want to see what will be the output when the clock is enabled. So now the clock is 1. So let's do the first row. So we have J is 0, K is 0, and Q is 0. And the clock is enabled. So J is 0, K is 0, and the current state is 0. So 0 will go into a location. It'll come here, and then it'll be an input to this NAND gate. So the bottom NAND gate, we completed the inputs 1 and 2 zeros, so the output is 1. So R bar will be 1. Now for this NAND gate, 0 and 1. For the AND gate, 0 and 1 will give us 0, but for the NAND gate, it's the opposite, so this output here will be 1. So Q bar will be another input for the top NAND gate, which is 1 here. So the top NAND gate, we have 2 1s and 1 0 as inputs. We go back to our table here, 2 1s and 1 0 input, the output is 1. So now S bar is 1 and R bar is 1. So if we go back to this here, the SR latch, so that means we hold the previous state. So the previous state is 0, we hold it, so the output here will be 0. And then you can complete the bottom 4 rows in the same way we did. You should be able to practice with it and conclude the next state. But let me give you the answers. So this will be 1, this will be 1, this will be 1, and this will be 0. Now we can come up with a generic truth table for the JK flip-flop. So let's do this. So now from these two, we want to conclude the final truth table for the JK flip-flop. So we have our clock input here. We have the J input, we have K input, we have Q is the current state, and Q plus is the next state. So first, when the clock is disabled, so as we saw in this whole table here, so we get hold for the next state regardless of J and K. So now we say we don't care about what J is, we don't care about what K is, we don't care about what the current state is. So the next state will be always hold. We hold the previous state when the clock is disabled. So now when the clock is enabled, let's see all the possible combinations for JK. So for JK, two inputs, we have 4 combinations. So we have 0, 0, 0, 1, 1, 0, and 1, 1. And then in here we have the clock is enabled. So the clock is 1. So we want to figure out what will be the next state. Q plus. When J is 0 and K is 0, so let's look back in our table here. When J is 0 and K is 0, this is in 2 locations. So if we look here, Q plus and Q are equal. So that means we are holding the previous state. So for this row here, Q plus will be hold the previous state. So next, when J is 0 and K is 1, so let's see what's happening. When J is 0 and K is 1, so we need to look in these 2 rows here. So in these 2 rows, regardless of the current state, the next state is 0. So that means for this row here, the next state will be 0. So next, let's see what happened when J is 1 and K is 0. So when J is 1 and K is 0, so we are looking in these 2 rows here. So regardless of the current state, whether it's 0 or it's 1, the next state is always 1. So that means for this row here, the next state is 1. And then the last row, when j is 1 and k is 1, so let's see what's happening. When j is 1 and k is 1, we are looking in these rows here. So let's see the q plus what's happening and compared to the current state, q. So we see it's the opposite for it. When the current state is 0, the next state is 1. When the current state is 1, the next state is 0. So that means for this one, we have toggle. So we toggle the previous state. Or in other words, it's q bar. It's the complement of q. So this one here will be the final generic truth table for the JK flip-flop. But it's very important to know how we can derive it rather than just like memorizing it. And then the symbol for JK flip-flop can be drawn as follow. So little box, we have a J input, we have K input, we have the clock, and then we have two outputs, Q and Q bar. So this is it on JK flip-flop. Thanks for watching. I hope this was helpful.
Enjoyed this video? Subscribe to the Computer Engineering Notebook for more tutorials on computer architecture, embedded systems, and hardware design. And hit the bell to catch the next one.